Hello everyone, I'm Jarin Taslim. Hope you all are doing well. Welcome to my class of Introduction to Digital Signal Processing. Before we start, I want to know what is signal? Do you know what is signal? So a signal is detectable physical quantity or variable that carries information. Like I am talking right now, a human voice, this is a signal. Television picture, this is a signal. Temperature, light, voltage, current, pressure, everything is signal. Mathematically, signals are represented as functions of one or more independent variables. If you want to see an example, you see here, this time is an independent variable and we have plotted the audio signal. This is a plot of human voice signal. Across time, this is changing. With time, this human voice is changing. This is a human voice signal. In this example, you see with time, current is changing, current is alternating. This is a current signal. There are two types of signal, analog signal and digital signal. Most of the signal that we come across in nature, voice, television, picture, temperature, or whatever it is always analog. But why do we need to process in digital domain? Why do we need digital signal processing? Why not analog signal processing? Because analog is available, so why not processing it in analog domain? We'll talk about it a few slides later. First, we'll see how can we convert this analog signal to digital signal. So there are two steps to convert an analog signal to digital signal. The first step is sampling and the second step is quantization. So in analog signal, both the independent and dependent variable t and x, both are continuous, means it can have any value. After sampling, we sample it after each t seconds. So the time t is discretized, but the x remains continuous. This is called discrete time signal. So after sampling the analog signal, in every t seconds, we get discrete time signal. Next, we quantize it, means we now discretize x also. Here, x can have only a certain levels of values, like 1, 2, 3, 4. But here, x could have any value. So if here any x value would be 2.9, it should be converted to 3 after quantization. Here, if any x value was 3.9, it must be converted to 4 here. Means x only can have certain levels of values. It cannot have all the values, all continuous values. So here both t and x both are discretized. And this is our digital signal. Digital signal means both t and x both will be discretized, both will be discrete. So how we are getting this? First, we are sampling this analog signal. Then we will get this discrete time signal. After that, we'll quantize this discrete time signal and we'll get the digital signal. In digital signal, both t and x will be discrete. So what is signal processing? Signal processing means we are changing the characteristics of the signal. We are analyzing it, modifying it, and synthesizing it. Some examples of signal processing are compression, signal filtering, enhancement of image, and so on. So now we'll talk about why we are choosing digital signal processing and why not analog signal processing. You see, in analog signal, both the signal is continuous, means it can have any value. So it is not possible to process this signal because no software can process it. But in digital signal, there are discrete values of X. So we can process it using any software like MATLAB, Python, etc. This processing can be done using any digital and synchronous processors. That is not possible for any analog signal processing. Also in analog signal, if we want to change something in signal, we have to change the whole analog circuit for it, which is not possible. And it is very time consuming. So in digital processing, it increases our reliability and accuracy. Also, the circuit designs are less complex and versatile. These digital signals can also be stored in digital storage media. So you see, there are various advantages of digital signal processing. That's why we are avoiding analog signal processing. First, we converting this analog signal to digital signal, and then we will process the signal in digital domain. So what are the applications of DSP? Digital signal processing have many wide areas of applications like audio signal processing, image processing, digital communication, speech signal processing, audio broadcast, media, music, audio storage. These all are audio signal processing. And for all this, we need DSP. Digital TV, digital radio, telemetry. For all this, we also need DSP. Now we will talk about the topic sampling, the first step of analog to digital conversion. So suppose this is an analog signal, and this sampling can be treated as a digital switch that will be on after every t seconds. So when the switch will be on, we'll get that particular value of X. Like this, we will discretize this analog signal. Here we will get the X values only t, 2t, 3t, 4t, and 5t seconds. Like this, we will get only in this particular seconds, we will get the X value. Not all values of t, we can get the X values. So if we normalize this axis, we can get 1, 2, 3, 4, and this t will be converted to n. So after discretization, this independent axis will be converted from t to n, and we will call this t, 2t, 3t as 1, 2, 3, 4. Like n have values of 1, 2, 3, 4, etc. Here n will be always an integer. This t here, we'll call it sampling interval, as after each t seconds, we are taking a sample from xt. So this t will be called sampling interval, and fs will be called sampling frequency, which is equal to 1 by t. So this is our discrete time signal, which is xn. Here the independent variable will be n instead of t. So xn equal x, t equal nt. Here, mind you, this third bracket indicates that this is discrete n, and this first bracket, this is continuous domain. So when in this means analog. So in analog signal, we will get t equal nt values of x. At n equals 0, t equal, at n equals 0, t equals 0, n equal 1, t equal t, n equal 2, t equal 2t, like this. So this is our analog signal, xt equal a cos omega t. Here omega is analog angular frequency, which is in rad per second, and it is capital omega. And this is equal a cos twice by ft. This f is analog frequency, which is in hertz. So if we now want to discretize it, what we know that if we want to discretize, we have to take the values in nt times. So xn equal x nt. So we'll put this nt instead of t here. So a cos twice by f, and we are putting nt instead of t here. So nt, and then this t will be converted to 1 by fs. We saw here fs equal 1 by t. So t equal 1 by fs. We are putting that here. So a cos twice by f by fs. Now this f by fs, we can write it as f, which is discrete time frequency, and its unit is cycles per sample. So this is our final discrete time signal, that is xn equal a cos twice by fn. Here you see the independent variable is n and its frequency is f. So what we have learned that first we will convert this analog signal by sampling, quantization and coding to this digital signal, and this is called analog to digital conversion. After analog to digital conversion, we will do discrete digital signal processing. After digital signal processing, we will again convert it to analog signal by digital to analog converter. Then we will get the processed analog signal. So we are computing less by using the digital domain. So our computation complexity reduces in digital domain. That's all for my today's lecture. Thank you, everyone.